right, so it wouldn't be practice problems if we weren't here working through it together. I've got my fancy little X Pen Padlet thing here. It's going to let me write down with my little stylus. I guess this is for blocking the signal. It works pretty cool. I don't know, I feel like I'm a professional pool player. I feel like I don't know. Anyway, so we're going to try out some of these practice problems here. So let's read through problem number 1 here. All right, so Jerome and Claire are doing the period of a pendulum lab. Don't worry about that. You don't have to do that. They observed that a pendulum makes exactly 10 complete back and forth cycles of motion in 21.8 seconds. Determine the period of the pendulum. Mr. T, I thought we were talking about waves here. What the heck is this? I'm not ready for a pendulum. Well, like we said, waves, they transfer energy through harmonic motion. And pendulums are harmonic motion, right? It's any kind of back and forth motion. So the equations we have for some of these other things, right, like period and frequency, we can use for any kind of harmonic motion. Wavelength, not so much, that's kind of more particular to waves, but frequency and period, that's it's measuring how quickly or how frequently any kind of back and forth harmonic motion happens. So we can use the same equations here. So we know step 1 is to draw a picture. I'm not going to worry about too much of that. For these, we're going to focus on steps 2, 3, 4, and 5. Variable list, equation, number, solve. But we are definitely going to want to mark up the problem. So here we go. So let's see. So first, I'm going to go down here, determine the period of the pendulum. It would also help if I did this. Oh, hey, that's cool. Let's go back. Let's turn the pen on. There we go. Let's change our ink color to something a little bit more Mr. T style. Yeah. All right. Cool. All right. So we got this. So we want to determine the period of the pendulum. So we can go here. We know the period is italicized T, question mark. We want to box that. Okay, let's see. They observe that, I know this one, 21.8 seconds, right? The time that it takes. That's a time unit. And then 10 complete back and forth cycles. What's a back and forth cycle? That's an oscillation. So we got 10 oscillations because we've got 10 back and forth motions. This is very hard to do. We will practice and get better at it. Okay, so if we make our variable list then, we got period equals question mark, oscillations equals 10. We don't have a variable for oscillations or waves or anything. T equals 21.8 seconds. We got 2 equations, right? We got if we bring it over here, we got V equals lambda F, and we got period equals 1 over frequency. They've given us none of those. So how do we do this? Well, one of the things we're going to do with wave problems, and we've done this a couple of times before, is we'll use the definition of something as an equation, right? So the period is how long it takes to make one wave. Or, like we said before, it's seconds per wave, right? So we can use that as an equation. Period equals how many seconds per oscillation, or how many seconds per wave. We know that there was 21.8 seconds for 10 oscillations. So that gives us a period of 2.18 seconds. Simple enough, which should make sense. This one's less about math and more about just kind of thinking logically, right? Like if it takes 21.8 seconds to do 10 of these, well, 1/10 of that should be the amount of time to do one. And that's basically all you do. So we'll erase all ink on this line, and we'll practice problem number 2. Alright, so we got Sachi is rocking to her favorite radio station, 92.9 FM. This means that the station broadcasts radio waves with a frequency of 92.9 kilohertz. In case you didn't know that, radio stations, their frequencies, their numbers, that's what it is. Their station number is actually the frequency that their radio waves are bouncing up and down at. So like 92.9, that's 92.9 kilohertz. The Sports Hub 98.5, that is 98.5 kilohertz of frequency. So your antenna can kind of tune into those specific frequencies and enhance those and amplify those that are coming through the speaker. ZLX 100.7, 100.7 kilohertz in frequency. Hot 106 or 96.9. I've been listening to that a lot lately. Your home of hip hop throwbacks and anyway, and the second date update, which is really problematic. But anyway, so those are the frequencies of the radio station. Or that. AM frequencies are a little bit different. We can talk about those later in a Zoom call or something like that. But yeah, that's what the FM radio dials are. They're actually the frequency of radio waves that are traveling there. So let's throw that down there, right? So we got a frequency of that. So that's our frequency. And now kilohertz, right? So that's kilo is times 10 to the third. But here we got this right here. So we got to be careful about that. Careful. Since radio waves and all electromagnetic waves travel through the air at a speed of this, right? So we talked about this before. The speed of electromagnetic waves is all constant. So that is that, V. In fact, the speed of electromagnetic waves is C. And this is C through air, not C through a vacuum. Wait, Miss G, I thought you said it was 3 times 10 to the 8th. Well, yeah, but that's through a vacuum. That's the fastest they can go through a vacuum. They get slowed down a little bit when they travel through different stuff. We'll do a whole puzzle on that later. So that's how fast they travel through air. So the speed of light, speed of electromagnetic waves is often known as C, right? So E equals mc squared. That's the C they're talking about, the speed of light, or speed of electromagnetic waves. And they want us to determine the wavelength, right? So wavelength equals question mark. Solve for that. Okay, so this is pretty easy, right? So they give us the V, right? So that's the V of the wave. So the V wave, the speed of this wave, is equal to the speed of electromagnetic waves in air. Okay, so let's throw it in. Right? So 92.9 times 10 to the 7th. We got that. Kilohertz. Frequency is that. Pop. And then, yeah, then you just plug and chug, right? So V wave equals that. V wave equals lambda F. 2.997 times 10 to the 8th equals lambda times that. Move them over. And if you're having any kind of trouble with your scientific notation, the search on YouTube. Right? Take a look, your brand of calculator scientific notation tutorial. And I'm sure someone will be there to show you. If not, come to a Zoom session and we can do it together. I'm lonely. Please come and visit me. So yeah. You should get 3.23 meters. Depending on how you round, you might get something different. But do we care about rounding? Not particularly. Not right now. Sig figs are not a problem for us. So you'll learn about that next year with your chemistry teacher. That's their problem. But that's how we do that. And if you're having trouble with converting frequencies and things like that, like in kilohertz, just Google it real quick. Just throw it into Google, like 92.9 kilohertz in hertz. You'll get it out that way. All right, erase all link on the slide. Let's go to the next one. Oops. Strong winds can apply a significant force to tall skyscrapers to set them into back and forth motion. Again, so we're in a harmonic motion. We're not talking waves, harmonic motion. The amplitude of these motions are greater at the high floors and barely observable for the lower floors. It is said that one can even observe the vibrational motion of the Sears Tower in Chicago on a windy day, which I think is not called the Sears Tower anymore, but oh well. As the Sears Tower vibrates back and forth, it makes about 8.6 vibrations in 1 minute. Determine the frequency and period of this vibration of the Sears Tower. Okay, so this is just a harmonic motion problem. So determine the frequency. Frequency equals question mark. And the period. Period equals question mark. And they told us here 8.6 vibrations or oscillations. Right? A vibration, oscillation. Keep using 2L. I should know that. In 1 minute. That's the time. Time equals 60 seconds, right? We gotta convert things. We all keep it in seconds there, all our time units, because our frequency and period units are usually in terms of seconds and hertz. Hertz is per second, so we gotta be consistent with that. And then just like before, we're gonna use the definitions as the equations, because again, they didn't give us anything else, so we gotta use those. Right? So frequency, and I'm just gonna solve for frequency first, because that's what they asked for first. Oscillations per time, right? It's how many seconds per wave, or how many waves per second you're making. So if I'm doing 8.6 waves in 60 seconds, it's a frequency of 0.14 hertz. Now at this point, you can do one of two things. The more legit thing that I taught you before is don't use rounded numbers, right? So we could use this formula here, period equals 1 over frequency. But to be a little bit more legit, we would probably want to use the data that we've got, so we're not rounding as much. So we should probably do 60 divided by 8.6. But in this case, just to get a little more practice with this equation, since we haven't tried it yet, I did it the other way. I just did 1 over frequency. I did that, and I got 7.14. You might get something a little bit different depending on which way you went about it, but again, as long as you went about it in a right way and did it with the right numbers and did not mess up your calculations, we are good. What do we round to, Mr. T? This was rounded to 1 decimal. This was none, and then you did 2, and you did 2. We got bigger fish to fry. Don't worry about it. Like, when in doubt, go 2 decimal places. That's kind of what we've always done. So, what happens? Let's do this. Next question. It's gonna get harder. Don't worry. Humpback whales are known to produce a collection of elaborate and repeating sounds with frequencies ranging from 20 hertz to 10 kilohertz. So 20 times per second versus 10,000 times per second. That's a lot. The sound waves travel through water at speeds of approximately 1,400 meters per second. Interesting. So sound waves travel at 1,400 meters per second in water. Cool, cool, cool. Determine the wavelengths of the sounds. Okay, so wavelengths. So we want, at the lower and upper range. Okay, so we got frequency 1 and frequency 2. All right, so we got F1 and we got F sub 2. And they want us to solve for the wavelengths, right? So, okay, so this is the wave speed here. The wave. I'm loving this pad. It's so much easier than trying to write with this. It still looks kind of sloppy, but I'll get better. And find the wavelengths, right? So we want lambda 1 equals question mark and lambda 2 equals question mark. Okay, pretend I circled that correctly. So yeah, so pretty plug and chug, right? So they gave us 2 sets of variables. I just said lambda 1 is what we want to look for, and that's a frequency of 20 hertz, and it's moving at a speed of 1,400. And lambda 2, which has a frequency of 10,000 hertz and a wave speed of 1,400. So remember what we said before about this inverse proportionality of waves traveling at the same speed? So they're traveling at the same speed. This one's got a lower frequency. This one's got a higher frequency. Which one's going to have the higher wavelength, the bigger wavelength? Lambda 1 or lambda 2? Better be this one, right? The lower frequency, higher wavelength, if they're going to be traveling the same speed. So let's check it out. See what happens. V wave equals lambda 1 F1. We plug in our numbers. We divide. Mr. T, this is the easiest math I've done all year. Should I really write all these steps? Yes. Yes, you should. Because, as we've talked about, the easier the math is, the easier it is to make a mistake in your head when you're going too quick. It's easy to accidentally multiply these numbers when you should be dividing them. It's very easy to accidentally do 20 divided by 1,400. So the more you write out, the slower, the more patient you are, the less mistakes you'll make. Just make sure you do that. And then it's the same thing over here. Same exact equation, just slightly different frequency each time. And then bam. Oh, hey, it worked, right? The lower frequency, bigger wavelength. Higher frequency, smaller wavelength. All right, let's make it hard now. Holy badoli. All right, a transverse wave is observed to be moving along a lengthy rope. Adjacent crests. Adjacent. That's a word. Adjacent crests are positioned 2.4 meters apart. Exactly 6 crests are observed to move past a point given along the medium in 9.1 seconds. Determine the wavelength, frequency, and speed of these waves. All right, so they want us to get wavelength. They want us to get frequency. Question mark. And they want us to get the speed of these waves. V equals question mark. 1, 2s, 3s. All right. Let's see. Okay, what do we do? Okay, adjacent means next to, right? We talked SOHCAHTOA, opposite over adjacent. Adjacent was the next to one. Adjacent crests, right? So crests that are next to each other are positioned 2.4 meters apart. Okay, I see what you're talking about here. So we'll disappear this for a second, and then we'll go to here. So the whole thing takes 9.1. Okay, so adjacent crests are 2.4 meters apart. So this is here. Well, wait, that's one oscillation, right? So that's just the wavelength. So they gave us the wavelength. They just want us to like explicitly say it based on our data. So we can just say, adjacent crests would be 1 oscillation equals 1 wavelength. And they're telling us that 6 of them pass by in 9.1 seconds. So we can figure out the frequency from that, right? If we do waves per second. So 6 crests divided by 9.1, right? No. Nope. Let's look at how many oscillate, right? So the timer starts when the first one passes, right? So we got these 6 crests. So let's count out how many, right? So we got 1 wave. Let's go to a different color. And now we got 2 wave to the next crest. This is a bad idea. So we're just going to go back to yellow. So that's 1 wave. This is 2 wave. 3 wave. 4 wave. 5 wave. How many wavelengths? 1, 2, 3, 4, 5 wavelengths. Because we start timing here, so that when the first crest goes by. So 1, 2, 3, 4, 5, 6 crests give us 5 waves. So that's how we want to divide it out. Right? So wavelength. So there's 5 oscillations in 9.1 seconds. The wavelength is just 2.4 meters. They just kind of told us that, so we don't really need to show any work for that. But for frequency, we can use our definition, oscillations per time. So 5 oscillations in 9.1 seconds gets us a frequency of 0.55 hertz. And then V wave equals lambda F. Usually you just plug and chug, right? The lambda times F, 2.4 meters times 0.555. 0.5555 is 0.55. Should give you a speed of about 1.32 meters. If you round it a little bit differently, that's fine, but that's how it goes. On the slide. Bam! Number 6. All right, a standing wave pattern is established in a 246 centimeter long rope. It's a very specifically long rope, I guess. A snapshot of the rope at a given moment in time is shown in the diagram below. So we paused it. And vibrations travel within this rope at speeds of 22.7 meters per second. All right, well, that's definitely a frequency. Let's go back to the pen tool. Let's change our ink color because that's a little bit lighter. Okay, cool. All right, so at speeds of that, so that's pretty obvious that that's the wave speed, V wave. But that's it, right? And so determine the frequency. Okay, all right. So frequency equals question mark. Still getting used to this pen. But we need wavelength, right? If we're trying to do that, so V equals lambda F. So, how do we do this? Well, here's how. How many waves do you see? 3. How long is that rope? 246. So how long is 1 wave? 246 divided by 3. I can't do that math in my head right now real quick. I'm too busy performing. So let's see. We got 3 oscillations, so let's plug it in like that. So we're looking for frequency. Lambda is 246 meters. Right, because we're at 246 centimeters, but we're trying to go meters per second, right? Pay attention to units, meters per second, centimeters. We got to convert that. So 2.46 meters divided by 3 waves gives us 0.82 meters per wave. So that's 0.82. That's 0.82. That's 0.82. They gave us the wave speed at 22.7, and at this point you should be able to just plug and chug. V equals lambda F. 22.7. 27.68 hertz. Cool? Cool beans. All right. Last problem. What should be the easiest, but probably was the hardest. So we got this problem about microbats, right? So we got this microbat that uses echolocation, meaning it sends out sound waves, bounces off stuff, and the bat can basically do the math in its head. It doesn't actually do math. It just kind of does more of like a kind of feeling gut math of knowing how far away it is based on how long it takes for the echoes to come back, the reflected sound waves. So the bat comes in, does its sonic scream at some rocks that are 12.5 meters away, right? So it goes, the wave goes, bounces back, bam, and we want to know how long that takes, right? So we know that it goes, and then comes back. And we know that the speed of sound, it said, in air is 345, which, wasn't there a problem earlier with water? It was 1400, and now in air it's only 345. It's slower. Get to that next week. So, we're looking for time. We want to know how long that took. Well, the distance, careful. We know that it went 12.5 meters there, 12.5 meters back. But we want to know, the problem's asking about, how long did it take to come back from when it screened. So we want the total time. So the distance is not 12.5. The distance is going to be 25, right? Because it goes 12.5 there and then 12.5 back. Careful. The speed there is that. It's like, okay, well, wait. We're looking for the time. Wait, hold on. What are we doing here, Mr. T? V equals D over T. V equals D over T. Like, wait, we use frequency, but like seconds per wave, but I don't know anything about that. And yeah. V equals D over T. Still a valid equation. The waves don't speed up or slow down when they're traveling in the same medium. So, and wait, what about if they're doing different media? We'll get to that next week. So V equals D over T. Just plug it in. 345 equals 25 over T. Flippy floppy. 0.072 seconds. So less than a second. Less than a tenth of a second for that sound wave to go and bounce back. Because again, sound travels pretty fast. 345 meters per second. That's fast. That's very fast. Right? We said the fastest humans had ever gone is 11,000. I mean, we've gone faster than that. Right? We've definitely broken the sound barrier. We can go faster than sound. We'll talk about what happens when you do that later. Sonic boom. But it's still pretty fast. Like, I talk, you hear it. There's no real delay. So that's it. What questions do you have? I've been, hopefully, if I did this right, programming in pauses for you can ask questions about specific questions after each one of these. But that's a wrap for week 1 of Waves. Let me know what you got.